Hooke's law and modulus of elasticity. Within the elastic limit, the stress is directly proportional to strain. Take a spring and suspend it. There is a needle for arrow mark over here, and there are the weights. We are placing the weights. If you keep on place the weights, of course, this spring will be expand. So how much maximum can expand? That's called as elastic limit. Within this elastic limit, the stress is directly proportional to strain. Stress is directly proportional to strain. Okay, so stress is equal to constant into strain, proportionality constant over here. Stress by strain is equal to constant. This is Hooke's law. Once you can take a graph on x-axis, load supplied, on y-axis, extension. How much load you are giving, how much expanding the spring. If you take a graph will represent this is Hooke's law. Now, modulus of elasticity, Hooke's law, both are same. Modulus of elasticity is equal to stress by strain. Modulus of elasticity we termed as a E. Now, units, Newton per meter square. Dimensional units, m1, L minus 1, T power minus 2 is the dimensional formula. Different types of modulus of elasticity. Different types of modulus of elasticity. First one, Young's modulus. Young's modulus Y. Second one, bulk modulus K. Third one, modulus of rigidity, that is eta. What is Young's modulus? Elasticity of length, which means take a rubber sheet, you apply the force, it will be expand the lengthwise. That we can call it as Young's modulus. Bulk modulus. The modulus of elasticity of volume. Modulus of rigidity or shear modulus, which means eta. This is modulus of elasticity of shape. Now we can learn that Young's modulus of elasticity. Now take a wire of length L. Apply the force, it expands to delta L. Cross-section area of a wire is A. Now, within the elastic limit, the ratio of longitudinal stress to the longitudinal strain, we can call it as Young's modulus. Lengthwise is expanding, so Y is equal to longitudinal stress by longitudinal strain. So longitudinal stress is equal to force by area. Longitudinal strain is equal to delta L by L. So Y is equal to F by A into L by delta L. Now that is equal to F by area of the wire, we can take it as a pi r square into length by delta L. Since L is equal to 1 meter, area A is equal to 1 meter square, delta L is equal to 1 meter, then Young's modulus is equal to the force. Now, stress strain curve for a metallic wire. On x-axis, we can consider strain. On y-axis, we can consider stress. The initial part OA of this graph, we are indicating that stress is directly proportional to strain. Up to point A, Hooke's law is obeyed. What is Hooke's law? Stress is directly proportional to strain. So A point we can call it as proportional limit. A we can call it as proportional limit. After point A, stress is not proportional to strain. It's a curve to AB line. However, if load is removed at any point between O to B, curve retraces the path of BAO. The proportion OB of the graph is called as elastic region. This line we can call it as elastic region. At point B, elastic limit or yield point. Point B, elastic limit or yield point. Stress corresponding to the yield point, we can call it as yield strength. At point B, this is yield strength SY up to point B. Beyond point B, strain increases. You can see that the strain is increasing beyond point B. It's more rapidly than the stress. If load is removed at any point of C, wire does not come back to along the path of BAO. It comes to the path of CE dotted line. Even in reducing the stress to 0, the residual strain is equal to OE. OE we can call it as permanent set. Permanent set. The fact that stress strain curve is not retraces by reversing the strain is called elastic hysteresis. If the load is increased beyond point C, there is large increases of the strain of the length of the wire. If the load is increased beyond the point C, there is large increase in strain or the length of wire. In this region, the constructions develop at the few points along the length of a wire. The point D is called fracture point. Point D, we can call it as fracture point. The region between B and D, the length of the wire goes on increasing even without any additional load. So the BD region, we can call it as a plastic region. Without giving any external weight, automatically the length is increasing from B to D. That's called it as a plastic region.